Okay guys, so let's proceed with example on finding the R value for a certain structure. So if you can see your textbooks, exercise 5.4, page 190, these questions give us a portions of composite bar which is made by different material. If you can see from the diagram here, it has a width of 3 cm and a height of 3 cm, and it has also the length of 4 meter. And then the first material actually only appear within the square blocks, and then the second material with second conductivity fill in this whole area. So assuming that this composite bar positions along the x-axis, so we are required to find the resistance between the square end from here to the other square end at the back. So if I want to draw the resistance to represent, you can draw as shown here. See? So we need to supply, or we need to have the E that actually propagate across the composite bar. So since the R is going to be measured or to be calculated along the x-axis, so by right we can simply generate the E field that actually propagate along the x-axis as well. And we know that this has a uniform cross section, so the E field also can be in uniform field. So if you want to draw the E field, you can draw as such. Let's say the E field in X component. So if you want to find the total R, the total resistance that due to this defined structure, we know that in this structure of bar we have two material, so and each material will have their own resistance. So we need to find one by one, and we need to combine the R value between these two. So since we are given the E field in that direction, so we can have the R equations as shown here. The R becoming a negative integrations E dot dl over sigma integrations E dot ds. And we know that in this structure we have two R. R1, which is due to the first material here, our first conductivity value, and the R2 is due to the second material here, our second conducting material. So let's find the first R1, the first R due to the first material. So we need to use this equation. So the R here, R1, is actually a negative integrations. So the E here, guys, actually has X component which is propagate along the X-axis. So you can simply put here EX in X components. And also the DL here, the refers to the E path that the E now is going through along the x-axis from square end at the back, square edge, to the other square edge in front. So now again you can just simply put here X dx, and the limit for this potential equations always from lower potential to the higher potential. So if you see from this diagram, when the E propagate from this side to the other side, it means that this side will have higher potential, more positive polarity, and here will have lower potential with less positive polarity. So now here again in the equation we know that down here it belongs to the lower potential. So lower potential appear at where? At L equal to 4 meter. So here going to be L, and then the up here is 0, right? So over sigma number 1 is shown here. So now again I have to find the E field, the EX in X component Alright guys, so now we are going to find the DS. If you see, DS is sample, the sample area that taken from here, DS. So we know that the E field will penetrate across the area of here, so you can simply change the DS here actually in X directions, and here become dy dz. Alright, since the E here guys is a uniform, you can simply delete this E because they are uniforms. So now let's plug in or substitute all the value. Now we're gonna have here a negative, the L here is 4 to 0, and now here we're gonna have dx and over the sigma number 1, and now let's put the first limit of the dy from 0 to 0.03, and also for the dz from 0 to 0.03 guys, dy dz, and we need to subtract with the area of this hole because within this hole we don't have any sigma 1 material, so just minus for the pi 0.01 square over 2. Okay, we need to have the effective area, which is we need to subtract with this small hole area as shown here. Okay, so if you proceed, we can just find the R equations or R value. The first one is going to be the 4 over the sigma number 1, and then the area of the square is become 0.03 squared minus pi 0.01 squared over 2, and we know that guys this sigma 1 is given as 5 times 10 power of 6, 10 power of 6. So you are going to find the value given as 974 micro ohm. Right, that's our first resistance, that due to only the first material of here, conducting material. So now the same procedure guys, you can find the R that due to the second material here is shown here sigma 2. So the R2 again using the same formula, you have here L over sigma S S2 sigma 2. So now we have 4 and sigma 2 given as 5.8 times 10 power of 7, and now the area for the hole given as pi 0.01 over 2. Okay, so now for this we're gonna have the value given as 878 micro ohm. Right, so if you combine them to find the effective resistance, which is R between R1 and R2, the R total, since before that we need to define either this R in series or in parallel. It can be defined or it can be determined by looking at the E directions. If you see that the E direction here actually is a parallel to the interface between these two material, so they are actually in parallel. Okay, if the E, if you see now, actually the E directions is parallel to the interface between first and second material, so they are actually in parallel. So we can simply find the R total by combining in parallel way. We can have R1 parallel to the R2, so R1 so R2 over R1 plus R2. So finally gonna have this equation become 461 1.47 micro ohm. Alright, so guys, this is the way how we can solve these problems to find the R total from this composite bar structure. Okay, so I hope you can try yourself, and all the best. Thank you.